That button went fast. So, IR. Uh, I wish I could say I liked this slide, but this slide just has a bunch of random information on it. I won't ask you to do any energy conversions. I do think it's relatively useful to have an idea about this energy to wave number relationship, which is actually kind of nice because it's a direct relationship. And that's ultimately what all these calculations are really talking about, is that when we look at an IR, the information on that x-axis is our wave number. And the wave number is not wavelength, and it's not frequency, but it's related to our wavelength. It's the inverse of the wavelength, and because it's the inverse of the wavelength, it's directly proportional to our energy. So the larger values you see, the more energetic that bond, and that becomes useful when we're trying to look at general ranges, which we can see in our stretching frequencies. The big one that I'm going to say is kind of a big deal to kind of remember or acknowledge would be if we look at our carbon single, double, triple. The triple bond shows up at the highest frequency, which means highest energy. That's our stronger bond. That bond takes a lot of energy to cause it to vibrate. The double bond, being slightly weaker, shows up at a lower frequency, single bond, etc. Okay? The other part that's particularly useful, I would argue, would be right in here and looking at our, what are you showing me? Oh, because I'm showing the frequency, not the wave number. Sorry, I should be highlighting the wave number because that's what you see in the IR. 1700 for our carbonyl and 1100 for our carbon-oxygen single bond. Okay, so the carbon-oxygen single bond shows up at a slightly lower wave number, which means it's easier to vibrate. Why is that particularly useful? Well, if we were to go through and look at a structure like this one, or actually let's switch it up, make it more obvious. Our carbonyl, except now we had a negative charge down here. And you won't see negative charges, but this is kind of the relevant part, makes this a little bit easier. We could see resonance behind this. And if we were to draw out that resonance structure, what we would notice is that that carbon-oxygen double bond becomes a single bond. So what does that mean? Well, the red one is still our preferred structure, but the value where that carbon-oxygen double bond appears is going to shift to lower frequencies because that resonance weakens the bond. So resonance can weaken that double bond, making it show up at slightly smaller values, which becomes one of the interesting things that I pointed out already when we talk about IR as a big overview. We don't want to memorize the absolute values of these things because those values will change when we change our structure. If we're aware of what things can cause those changes, we can start to predict where things might shift or slide if we had things like resonance or other contributing factors. We could look at the atomic mass one. That's not that big a deal to me. What's more important is recognizing that resonance effect, but we can see it with atomic mass. We can do that comparison with HC versus HD. HD is a heavier atom and moves to a lower frequency than the CH. So if we think about, again, our IR as a bond vibration, if it's a lighter atom, it's going to have a higher frequency because it can move easier. If it's a heavier atom, that's going to be a harder thing to kind of stretch, and we'll see a lower frequency in our stretching. Okay, so those are the kind of big lessons behind the stretching frequencies. Watch out for resonance and consider the weight of your atoms. I don't like the weight analysis quite so much, but the resonance is a big one. I think I've said now a couple times, so you might expect that question. The next one, IR is really keying in on bond dipoles. So when we look at the IR, we've got those individual ranges, but then you might have also noticed that we see different intensities. Okay? So for instance, the carbonyl is a very, very carbon-oxygen double bond is a very intense stretch. whereas the carbon-hydrogen can be much less so, right? And what that's due to is the dipole moment. The carbon-oxygen double bond has a very large dipole moment because oxygen versus carbon. So a difference in electronegativity is huge, which causes a very intense signal. Carbon versus hydrogen, electronegativities are almost identical, which then means we don't get a very large dipole. It's hard for the IR to actually pick it up. Okay? So it becomes IR inactive or IR invisible. So bonds that have a larger dipole moment will be more intense. Bonds that have a smaller dipole moment will be less intense. So this could get asked both directions. The kind of trick one that typically shows up in a lot of spectra, or in some spectra, I should say, would be the IR inactive one. Okay? And that's if you have a perfectly symmetric system. Symmetric typically only happens around the triple bond. And if we were to say, look at, that's a little too simple, let's make it a butyne. The triple bond disappears. Okay? It is inactive due to the perfectly symmetrical stretch of that structure. That signal disappears from the IR. Okay? And we can make similar arguments that for those of you in lab might like to reference, that if we looked at a double bond, say like in blue, versus a double bond, say like in orange, both of these structures are going to have the same IR signals, but the intensities should be expected to be different. That orange one is much less symmetric on that bonding axis because we're looking at hydrogens versus carbons. Whereas if we look at the other one, yes, it's 2 carbons, but I get 1 carbon out that end as well. So that blue one, we might expect to have a weaker intensity signal, whereas the orange one might be a very strong signal. That could come in handy if you're in lab. It will come in handy. Lab reports, just so you know. Okay, so symmetric triple bonds tend to be the big signifier for this, and it usually trips people up because you don't see it in the IR. Where you would know that you had the triple bond is you'd use your mass spec to determine that you had more carbon atoms than your spectra actually allowed, okay, or that it appeared to allow. With that, sweet, look at that, sub 10 minutes, it's a record. I should probably stop the video. Maybe I'll let it run for half an hour now. I'll just stare.